This is the second video for CHEN 3130 Continuous Assessment 2 for question 1 that will talk about the heat transfer in pipe design optimization. So to find the rate of the heat transfer from the pipeline to the soil, so we know that from the first video we have found the optimum depth of the pipe to prevent ice formation of water inside of it, as well as the thickness following the European standard specification. Now we need to calculate the heat loss from the pipeline and ensure that it is compensated for by the heat gain from the soil, as they are equal to each other. This can be done using the concept of cylindrical conduction heat transfer rate using the Fourier equation for thermal conduction, as shown here on the left hand side. Now Q is the rate of heat transfer, K is the thermal conduction of the soil, L is the length of the pipeline, which is set to be 3.5 meter. T1 is the temperature of the water inside the pipeline, which is 273.5 Celsius, and the temperature of the soil, which is equal to 278.15 Kelvin, and R1 and R2 are the inner and outer radius of the pipeline, which were found to be equal to 0.08 and 0.08512 meter respectively. Now, filling in all these information in the equation, we will find that the rate of heat transfer from the pipeline to the soil is equal to, or the heat loss is equal to minus 6898.183 watts per meter. So to calculate the maximum heat loss from the pipeline, we need to calculate the maximum heat loss from the pipeline during the coldest period, where the soil temperature is at its minimum of minus 5 degrees Celsius. We also need to ensure that the temperature of the water inside the pipeline does not drop below 0 Celsius, so we'll assume a minimum water temperature of 0 degrees Celsius for worst case scenario. Now the Nusselt number, which is the ratio of the convection heat transfer to the fluid conduction heat transfer under the same condition, will need to be found first. The equation of it is equal to 0.023 multiplied by the Reynolds number to the power of 0.8 multiplied by the Prandtl number to the power of 0.4, where this number indicates the correlation between the viscosity of the fluids and its thermal conductivity. Now, finding the Reynolds number, we will find the density of the water, and assuming a flow rate of 0.8 by the inner diameter of the pipe where the actual flow of the water occurs, then the viscosity of the water at 0.001 will give us 16,000, which is greater than 4,000 where it is a turbulent flow. And thereafter the Prandtl number, which is the viscosity multiplied by the heat capacity divided by the thermal conductivity, which I've seen here, which is equal to 7.450. Now that number, the Prandtl number, indicates that the heat exchange by the fluid momentum is preferred over the heat transfer via a thermal diffusion, which is the 7.45 indicate. Thereafter, I will add all the variables known, and we get the Nusselt number to be equal to 118.54. Now the number indicates that the pipe undergo an efficient heat convection with turbulent flow, hence why we have Reynolds number is greater than 4,000, with a turbulent flow in the 100 to 1,000 range. Next is finding the heat transfer coefficient between the water and the pipeline, expressed in terms of the NU, or forced heat convection transfer. Using this following equation, we will get a value of 415.63 watts per meter cubed Kelvin. Now, using the heat transfer coefficient of air from the first video at a value of 4.35 watts per meter cubed squared per meter squared Kelvin, we can calculate the overall heat transfer coefficient between the pipeline and the environment. Now, just for visual demonstration, what we're trying to do for the maximum heat loss is finding the heat transfer coefficient for the three sections here. So first is between the water and the pipe, which is convection. Second is the pipe and the soil, which is conduction. And third is the pipe and the air, which is convection. Now this is just to be able to break down the entire system from the pipe to the environment. Now on the left hand side, this is modeled through the following equation. So we need to find the overall heat transfer coefficient, which is going to use 1/u equation. Now as you see here, this is for the convection, this is for the conduction, and this is for the convection as outlined here as well. Now filling in the variables that we have already in this equation, we get a value of 1/u equal to 0.406056, and then finding the inverse of the value, we'll find the overall heat transfer coefficient equal to 4.15696 watts per meter squared Kelvin. Now finally, to find the maximum heat loss, which is the maximum heat transfer from the pipe to the environment, we use the following equation. So to find the maximum heat transfer will be equal to the cross-sectional area of the pipe multiplied by the found value of overall heat transfer coefficient multiplied by the difference between the temperature of the water minus the infinite temperature, which is basically the environment. Now, knowing that the cross-sectional area is equal to 2 pi, the inner radius of the pipe multiplied by L, note that in other cases this can be changed, but since there is only an inner radius thickness and outer radius, we will focus on the inner radius that the water flow occurs in. And then filling in all the variables that we've known, that we have where the temperature is in Kelvin here as well, we found that the maximum heat loss is equal to 1272.3, which is also equal to 1272.3 joules per watts. Now this is the references used in this video. This marked the end of the video. Thank you for listening.